Hello everyone and welcome to another Wrth Electronic eiSos webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is selecting the right coils for wireless power transfer systems. Our speaker today is our consultant for wireless power transfer, Würth Elektronik. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You'll be muted during this webinar today. This means that you can't ask us questions via your microphone. Nevertheless, you have the opportunity to ask us all your questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. Also, you can watch the recording of today's webinar a few days later on our website under the navigation point Webinars or on our Wrth Elektronik YouTube channel. Now I will hand over to our speaker, Jörg Hanschel, and I wish you an exciting webinar.
Yes, hello. Also from my side, a very warm welcome to the webinar. It's very kind of you to have interest in our wireless power topic, and we would like to help you to choose the right coils into when you are integrating wireless power in your devices or applications. What I would like to talk about today is the applications and the impact coils have there, technologies and standards you can use for wireless power transfer. Then the main topic, the coil-specific considerations you have to take care of. And the last point, how can Wrth Electronics help you in integrating wireless power in your device? Let's start with a very short, brief history about wireless power. This is not rocket science. Also, Nikola Tesla, more than 100 years ago, started with the technology. Then it was a little bit quiet around with some niche products, and it took off in a consumer product with the electric toothbrush in the 1980s. Then with all the, let me say, power problems we face still today in having enough power in our smartphones, the Wireless Power Consortium was founded with the G standard in 2008. And then first smartphones with integrated G receiver came out in 2011. And everybody was looking, what will Apple do? So I'm very happy that Apple decided 2 years ago to join the G standard of the WPC. And so I think for these small power levels, we have now, let me say, a valid, robust standard. But I come to that also in a minute. And the last point on the bottom of the slide is that now also charging of EVs is becoming more and more interesting, doing this without the big cable and doing it wirelessly. So what are the applications which have an also impact on coil size and coil positioning? So in automotive, we have charging smartphones in the car, which most of the car manufacturer offer currently, I think, for a lot of models. but also, as mentioned, the charging of EVs, for example, in a very much higher power rate and with totally different coils. Then we have the, let me say, infrastructure furniture area. This means currently mostly charging smartphones in tables, in hotels, in restaurants, in airports, in meeting rooms. So, but this can also be, let me say, widened to other devices as well. A field where the technology is really beneficial is medical, where you get rid of charging contacts, which helps a lot in complete sealing devices and sanitizing those devices. I have some examples a little bit later. And also in the industrial field, in harsh environment, underwater, in explosive areas where you can get rid of galvanic contacts and have a safe usage or transfer of power. This is an application from the medical field with an hearing aid with an implant. So Cochlear has an implant which has no battery, but has the, let me say, connections to the hearing nerves, and all the, let me say, sound processing is done by this device, which is attached with a magnet to the head of the human being. And data as well as energy for the implant is transferred via specific coils in that application. Another example out of the field of underwater is this diving computer, which is completely sealed, has the coil on the backside, but also the transmitter is completely sealed. Here you can see here the transmitter, so you can charge the computer even underwater or in a very wet environment. And this is an example from sports. In the National Ice Hockey League, there will be this new electronic puck used in the upcoming season. The purpose is to locate the puck during the game wherever it is. It is a quite fast thing, this puck. And currently, it's hard to follow, let me say, the curve of this puck. And so there's an electronic inside which where the puck can detect it in real time with the receiver coil, and you see also in the transmitter coil. And why choosing those coils in that, for example, in such an application? This will be topic of the webinar. But this were now the, let me say, examples for smaller power, but it's also the technology is beneficial for higher powers as well. So the Wireless Power Consortium is working to create a standard in the 60 to 200 watt area and in the 200 to 2.4 kilowatt area with a cordless kitchen project. So you see here prototypes of kitchen appliances which can be supplied with energy, for example, through the tabletop, and this goes up to 2.4 kilowatt, and it's not charging, it's directly using the energy in the appliances. Yeah, what technologies are used and which have an awesome impact in the design and the, let me say, shape and parameters of the coils. We have, in principle, in the market, two areas. One is the closed-coupled inductive power transfer, which means cutting a transformer in half, doing the primary coil as a transmitter and the secondary coil as a receiver, and so the energy is transferred. The other possibility is on the right-hand side is a resonant power transfer. So you have at a resonant frequency on the transmitter antenna, you, let me say, supply the energy, and the receivers, one or more, can pick up, if they are tuned to the same frequency, can pick up the energy out of the field. Here are two examples for that. So this is the receiver coil over the transmitter coil, which normally lies directly on the coil. And for the resonant power, here you see on this one transmitter coil or antenna, you see three receivers at the same time with different coils or with different antennas which pick up the energy. So this is where we are in with wireless power transfer. And in the following, I will concentrate on this inductive power transfer or closely coupled. So if you are trying to integrate wireless power into your device, you have to answer yourself a couple of questions in the beginning. Oh no, first, I would like to talk a little bit on the standards. So we have this closely coupled standard, which is the G standard from the Wireless Power Consortium, which is working at a frequency from 100 to 200 kilohertz and has two profiles, a base profile and an extended power profile with 5 and 15 watt. And as mentioned before, we have the higher power classes planned to up to this cordless kitchen project with 2.4 kilowatt. And the other standard which is in the market is from Air Fuel Alliance, a resonant standard, which uses a frequency of 6.78 megahertz. This is an ISM band where you can transfer energy. And uses low power Bluetooth for the data communication for the power management. These are the two standards which are in the market, but from, let me say, market size, G standard, since Apple decided to follow the G standard, is the, let me say, most popular standard. How does wireless power close coupled system look like? You have a power source somewhere in the transmitter, you have a converter, and then you have this resonant tank, which consists of the transmitter coil and the matching capacitor. And on the receiver side, you have the secondary resonant tank with the receiver coil and the matching capacitor. Then you have a rectifier, and then you have your load. So this is in principle the basic components of a wireless power system. And now I come to these coil-specific considerations. What you have to check is, what is the power level? This is the first question you need. If you are below 15 watt, then you can use, for example, an off-the-shelf G solution. If you are above 15 watt, you have to make a proprietary solution according to the power level you need. Then what is your available space within your receiver, so that what fits in to make the wireless power transfer happen? What is the distance between the transmitter and the receiver, which also has an impact on the system and also on the choice of coils? The freedom of positioning of the receiver on the transmitter, I will come to details on that in a minute. Then the electrical performance, which you would like to have, the efficiency, the shielding, the performance, and of course the price of the solution. So let's now have a look in some of those parameters where it is important to choose the right coil or coil combination. So if you have your system under control. So means you make sure that your receiver with this coil is always placed exactly on the transmitter coil. Then you can use such a single coil system like on the left hand side. If you need freedom in one direction, you can use such a coil array like in the middle. For example, all the smartphone chargers in cars are using that approach. What is the reason behind? The reason behind is if you put your smartphone on the charger in the car, and then you have to brake heavily, or you accelerate very fast, like if you have a Ferrari, then it might happen that your phone will move on the charger. If it is on a single coil charger, it will stop charging. If it is on that three coil array, the system will detect if the coil moves, let me say, from this space to that space, and it will deactivate the first coil and then activate the new coil where the receiver is placed. If you need more freedom in the direction, you can use such a coil array where you can place your receiver somewhere on that coil array, and the electronics will choose the right coil and activate the coil which fits best to the receiver put on that. So you have a solution. It might be a little bit more complicated and costly, but for placing the receiver on the transmitter, you have solutions, but this has also an impact which coils to choose. Another thing which is often forgotten or not given the, let me say, enough attention is the misalignment. What can happen? You can have a lateral misalignment. This you can overcome with the solutions before. Let me say, vertical misalignment is the Z distance between the coils, which you have also to have under control. But what I would like to talk about is this angular misalignment, and this could have a really nasty impact. I give you an example. If you put your receiver correctly and optimal on the transmitter with zero angular misalignment, then you can reach with a narrow Z distance, you can reach a coupling factor of around 0.9, 0.95, which is quite ideal and has a high efficiency. If you then create an angle of 40 degrees, for example, then your coupling factor drops to 0.4, which means less than half. So you are losing more than half of the efficiency of the system by not changing anything in the electronics, but only mechanically create this 40 degrees angle. So this is also a point you should have into consideration when you are creating your system. Another question we often get, why do we need this ferrite shielding on the coils? Will the power transfer also be working without the shielding? Yes, it will. Here you see the air coil and the magnetic field around the air coil. So if you put the receiver as well in that field, you can transfer energy, but you see from the dissipation of the field, you will have a lot of losses. Then if you go to the shielding of your, for example, transmitter coil, you see the field is now guided and focused on one side, and it's also stronger here. And if you have on the right-hand side shielding on the transmitter and receiver, then you have the really big advantage that the field is concentrated between the coils. So you have a high efficient power transfer. And not to forget, you have also very good performance in EMI, EMC questions, which that you have the, let me say, field under control also from EMI, EMC perspective. Also an important point in choosing the right coil combination is the coil area. The coil area has to fit. The ideal, let me say, power transfer, wireless power transfer is if you use the same coil as a transmitter and as a receiver, which is, for example, done when you are charging EVs or this high power systems. But here we have an example for Qi. This is a Qi, standard Qi single coil transmitter coil, has a diameter of around 50 millimeters. And these are 3 receiver coils which work perfectly with that coil. It transfers also the energy, but let me say the efficiency is different. You see with on the left-hand side, you see a coil which has nearly the same size like the transmitter coil, so you can reach a coupling factor of 0.8, which is quite good. If you have not this square area in your receiver and you need more a rectangular, like in the middle example, then you can use it. It's no problem. It will work with the Qi solution, but you get a lower coupling factor due to the fact that the coil area ratio is a little bit not so good like in the other case. And if you have to take a smaller receiver coil due to the fact that your receiver, for example, is smaller, and here in that example we have a 1:2 ratio, then the coupling factor also goes a little bit lower. But if you would, we have, and this is coming also from a lot of customers which say, okay, I would like to take a Qi solution, but I have only, for example, in that case, 19 millimeter diameter for the coil space in my receiver. Will it work? With a standard Qi transmitter, it will not work due to the fact that you have a coupling factor of 0.29 and a area ratio from 1:6. But we can help in that case. We have a coil, a transmitter coil, which has the same inductance like that coil. So that if you then take, let me say, the electronics of a Qi transmitter and only replace the coil, the transmitter coil, then you are back to a coil ratio from 1:1 and a coupling factor of 0.6, and then it will work again. So this is an area where we can help on that, but you have to take this into consideration. And that this is an example from Apple. This is the breakdown from an iPhone 8. And you see that Apple did everything correct. They used really the area for the coil. So the coil is quite thin, that's okay. But the coil is also has a huge area. So this makes sure that the iPhone has no problems with charging on the standard Qi transmitters. So this as an example, as a successful example, how to choose the right coil for the application and the environment. Yeah, and there are some other points as well to, let me say, look at but in terms of the given time, I would like to stop with those main points here and would like to talk a little bit about how Wrth Electronics can help you to make an optimal integration of wireless power in your device. So our coils are fulfilling the G standard, and above we have an efficiency of between the coils of more than 90%, and we have a very good performance due to the fact that we have a high quality Litz wire and high quality ferrite material, which helps also in all of these shielding topics. We are the coil supplier which offer more than 30 transmitter coils and 27 receiver coils currently. So normally you should find a coil which fits your needs or coils which fit your needs. But in the case you have other requirements, we are doing also customer specific coils, like for example with this hearing aid example I showed you before. We are also doing customer specific coils. So you give us your requirements, we simulate this and come up with a proposal to start with. So yes, we are doing also a lot of customer specific coils. Then another point where we can help you, this is now above G. So if you are planning to make a wireless power system with up to 200 watt, we have a development kit which is outside the standard, which is a proprietary solution together with a chipset from Infineon. But the also point which is in here that you can transfer user data from the receiver to the transmitter, because this was a question or a request from a lot of our customers that they would like to transfer via the coils their few user data and not needing, let me say, a Bluetooth connection or what else to transfer the data. So this is also a point where we can help you with also with adaptations when you start with this kit with other coils. And going back to G, we also have now a new 15 watt G EPP development kit together with IDT. We had already one before. What is the new thing here in that kit? That kit also contains, besides the transmitter board, the power supply and the receiver, also a dongle where you can connect it to your PC, and then you can monitor the data flow between the transmitter and receiver. So you don't need any additional hardware. This is done by the IDT chipset and the application you can download on your PC. So these are the things we can offer you. Another point where you can find a lot of information and also some videos on wireless power is on our wireless power website. There is also the template for the customs coils. One tool I would like to mention which is important is our mix and match tool for G solutions. So we have all our receiver coils and all our transmitter coil combinations listed here. And if you find a green dot, then you can use this combination, this coil combination. We tested it, it will work perfectly with a G reference design. If there is a red dot, don't even try it, it will not work, mostly due to the fact, what I mentioned before, that the coil area size ratio is not fitting. If there is a yellow dot, it might work with some restrictions. So if you would like to use this combination, please ask us and we can give you some advice on that. And if you are on this mix and match site and you click on one of the green dots, then you end up in our Red Expert, which is our very powerful tool for all our products. You see then here you're choosing coil combination. You get some additional diagrams, but the important point is this one. This is the calculation for the capacitor values in the resonant tank. Why is this important? So if you are using a G IC reference design, the IC manufacturers, they are using in their reference design a certain coil, and they are dimensioning their reference design based on that coil. If you are using this reference design but choose a different coil due to the, let me say, your requirements or the space you have in your receiver, then you have to adopt this serial and this parallel capacitor so that the receiver, the G receiver, will work properly. And these capacitor values are depending on the inductance of the coil. And for all these coil combinations, we put these capacitor values here so that you are sure that if you choose a different coil in the reference design, that you get a well optimal functioning system here. So this is also a support which you only get from Würth Electronics. And last but not least, we have also a new book in our trilogies, also on the wireless power transfer. We have this book, which also gives you the basics and let me say, applications to start wireless power transmission in your device or in your development. Yeah, this was it from my side. I thank you very much for your interest, and I'm looking now forward to answer your questions in the next quarter of an hour.
So thank you very much, Jörg, for this interesting webinar. We are now starting to check all your questions. In the meantime, I would just want to say thank you for your participation, and you are receiving the presentation as PDF and also the link to the recording of this webinar today in a few days from us once again in a separate email. So if you have any questions left or you just want to see the presentation and the webinar once again, you can just check this via your email, and otherwise we will still be there for you via email. You can just email us if you have any questions or contact your sales representative. We're always here for you. So let's check the questions. Jörg is going to check the questions and also answer them directly.
Yes. Okay, so question, is bidirectional energy transmission possible? If so, what should be considered? Bidirectional energy transmission at the same time is not feasible, but you can, in proprietary solutions, we have an application note on that, where the transmitter electronics and the receiver electronics is the same. You can then change also the energy transmission, but not at the same time, that's for sure. So then question, in wireless phone charging, if you do not know the resonant frequency of the receiver side, in case the iPhone, how do you approach it? Okay, so in wireless phone charging, let me say, the frequency is given by the G standard. So because currently wireless phone charging is done, and especially if it's integrated in the phones like the iPhone, it is done by the standard. So normally for example, the systems work around 125 kilohertz. And the standard, if a product, so for example the iPhones and also the transmitters. If they are G certified, they have to follow the standard, and the certification ensures that every certified receiver works with every certified transmitter. So this is the, let me say, idea of this interoperability G standard. I hope this answers that question. Then, are there solutions how to transfer data and load at the same times in G standard? Yeah, good question. The point is, up to 2 years ago, the G standard was a closed standard, and the data which was communicated via the coils was only for the power management. This was out of the reason that the radio approval was then not necessary. But the authorities changed that 2 years ago globally, and now also G devices have to have a radio approval, and therefore now the consortium is working to widen the standard so that also user data can be transferred. And the first step, for example, is this new 15-watt kit we have with IDT. So, and another thing, yeah, this was also approval. What I just mentioned is, do we need a radio approval for a G standard application? Like I mentioned, yes. You need radio approval. For example, in Europe, it's the RED directive, RID, and I think in the US it's FCC. So I think all the countries have their regulations on that. Yeah. So these were the questions. So I thank you very much for your attention, and I would like to close here the webinar, and thanks a lot and have a nice day. Bye-bye.